but I'll think of something to help you out with this if you miss. All right, we're back online. So your unscheduled break is over. Let's get back into it. All right, so getting back into what I was talking about before we had this unfortunate glitch in the software. Electrons do exhibit wave-like behavior, and one wave-like behavior that they exhibit is called diffraction. So diffraction was something that had been observed for light and other forms of electromagnetic radiation for a long time, but it also happens with beams of electrons. So diffraction is scattering of light by a regular array of points or lines. You likely, if you took high school physics, did diffraction experiments where you held up a little diffraction gradient of light and you saw the light kind of scattered out in all directions. And it also turns out, which wasn't obvious until they showed it, that electrons can also be diffracted. Now they can't be diffracted as easily as visible light for various reasons, but if you take electrons and you put them through a crystal, so we'll learn later on that a crystal is just a collection of atoms that have very regular spacings between them, so they behave a lot like a diffraction grating with these regular planes and spacings. The electrons will be diffracted by the crystals. All right? So electrons are diffracted by crystals, and that was an experiment that was done later on to sort of demonstrate this wave-particle duality, that even though electrons are conventionally thought of as particles, they do exhibit this wave-like behavior that's been observed for also electromagnetic radiation. All right, now why is this important? Because this seems, again, pretty far out. This is more like a modern physics course at this point as opposed to chemistry. The reason this is important is because to really fully understand the behavior of electrons and atoms, we need to at least appreciate this wave-particle duality and the idea that electrons will have both wave and particle properties. All right, so now talking back into, actually I have a couple sample problems first, so let's not jump the gun on this. So let's do a couple of sample problems on what we just learned, and these are, again, just using those equations primarily is what we're going to be seeing in this part of the course. So if I have a red laser pointer, which is a pretty common one that people have at home to entertain their cats and things like that, these commonly available red laser pointers have a wavelength of 635 nanometers. So again, that's towards the long end of the visible spectrum. What is the energy of one of these photons? All right, so again, the energy of a photon is given by h times the frequency. We also have the relationship between frequency and wavelength that we learned. So again, there's two forms of this equation. In reality, there's only two equations you have to know. This one and that lambda times frequency equals c, and you can derive one from the other. So in this case, we'll use this form of the equation because we're given the wavelength. So the energy of the photon, we just start plugging things in. Planck's constant is also on your periodic table. That's h. That's 6.626 times 10 to the minus 34. And the units on that are weird, joules times second. Speed of light, c, still the same constant, 3 times 10 to the 8th. But once again, if we're going to get the energy of a photon and we're using wavelength as part of the calculation, the wavelength still needs to be in meters. So don't forget this conversion step where these constants are defined in terms of the standard SI units, joules, seconds, and meters. So if one of your units that you're using is not that, you have to convert it. So in this case, we need our wavelength once again in meters, just like we did before. 635 in this case. And the common conversion factor we use a lot is 1 meter is 10 to the 9th nanometers. Nanometers cancels out, and again we get on the order of 10 to the minus 7th, which is common for visible light. All right, so not much more complicated than before. We just have to, read the problem closely to make sure we're solving for what they asked for, which in this case is energy. So we get 3.13 times 10 to the minus 19 joules. All right, because our seconds cancel out here, meters cancel out, and the only unit that's left is joules, so it does indeed give us the energy of a photon in the standard SI unit of joules. Well, that's a very tiny amount of energy, so this beam of red light is not going to just have that energy. It's going to have a lot of photons that each have this individual energy. The total energy would be the additive sum of those. that comes out of the laser pointer. So if you have I think a typical laser pointer is around like 1 milliwatt is I think a common one. Maybe that's even too strong for home use, but it's around that value. So you're going to get something like 10 to the 15th, 10 to the 20th photons per second. So you have a lot of photons coming out of this thing. Each one has a very tiny amount of energy, but the collection of all of them has a significant amount of energy. All right, one more example problem. We're just taking things a little bit further here. So as we saw in the last problem, the energy that we calculate using E equals h times nu, or E equals hc over lambda, that energy is the energy of a single photon. Now let's suppose we want to produce 2 joules of energy using 520 nanometer light. So if you have a green laser pointer, the wavelength is going to be about 520. That's the sort of middle part of the visible spectrum. And if we wanted to generate 2 joules from that, how many photons do we need? So this takes things a little bit further than we did last time. Now our first step is still going to be to calculate the energy of an individual photon. Because if we want to know how many photons do we need to get this much energy, we need to know how much energy does each individual photon have. So we're going to use the same equation, hc over lambda, recognizing that this just gives us the energy of one single photon. So same constants, h, c. I will be lazy at times and write just 3 times 10 to the 8th. Keep in mind that it does have more significant figures than 1, but writing it as 3 is fine. And then this time, again, the wavelength has to be in meters, so we convert our 520 nanometers to meters by dividing by 10 to the 9th. And we get 5.2 times 10 to the minus 7 meters. All right, and so when we plug those numbers in, we get that each photon has an energy of 3.82 times 10 to the minus 19 joules. So that's the energy of one photon. We see that's a bit higher than the last problem. So the last problem was red light, which is on the low energy side of the visible. This is a little bit higher energy than that, as we would expect. And then if we want to calculate the number of photons that we need for 2 joules, we can almost use this, or we are going to use this really, as a conversion factor. This is the energy of one photon. So if we're trying to generate 2.00 joules, we want to figure out how many photons that is. We know that one photon has an energy of 3.82 times 10 to the minus 19 joules. Or we could have set this up as sort of a proportionality if you prefer to do it that way. It works the same way. But we use this as a conversion factor. Joules cancel out, and that gives us then the number of photons we would need. And it comes out to 5.23 times 10 to the 18th. Alright, so 2 joules is not a terribly large amount of energy, and it takes a lot of green photons to generate that. So that's a huge number, obviously. And again, driving home the point that these photons, even though they are quantized, even though that is the smallest unit of energy you can have for that wavelength of light, they are still a very small unit of energy. It's not a huge amount, obviously. So there's still a lot of photons in a typical situation that you would observe macroscopically. All right, so that's takes us to the end of that. Here's one more to try on your own, but I'll just work through it real quickly here. I'm going to have to keep track of the time because my video is not accurate anymore. All right, so let's say we have the work function is the minimum energy required to emit an electron from a metal surface. So that's related to that threshold frequency that we talked about in photoelectric effect. If the work function of rhodium is 7.98 times 10 to the minus 19 joules, which of these wavelengths of light will eject an electron from rhodium? All right. So the concept here, again, asks us a little bit, this is the photoelectric effect. We're shining light on a metal surface, ejecting electrons, and we want to know which of these photons, 225, 325, 175, or perhaps more than one of those, would be sufficient to eject an electron from the surface of this metal. So the concept here is that the energy of our photon, in order for us to eject an electron, has to be greater than the work function. All right, and this is just another way of stating that the frequency of the photon has to be greater than the threshold frequency. Those two are directly related to each other. So this is what has to be true. The energy of the photon we have, again, we're using wavelengths here, so we know that the energy and the wavelength are related by hc over lambda, and that has to be greater than the threshold frequency. So then what we want to do is let's solve for lambda. If we move it to the other side, that means lambda has to be less than hc over a0. So we just rearrange this equation, and now lambda is now less than that. It has to be less than this ratio. And we just plug in the numbers. So 6.626 times 10 to the minus 34. 3 times 10 to the 8th meters per second. And then E0 is that threshold energy, which is 7.98. All these are given to us. We don't have to calculate any of these. We just have to solve for wavelength now. So what we get is 2.49 times 10 to the minus 7 meters. And then if we multiply by 10 to the 9th to convert that back to nanometers, because all of our answers are in nanometers, we get 249 nanometers. And the key point is that our wavelength must be smaller than that, okay? Because when we rearrange the inequality, that's wavelength goes to the other side. Another way to think about this is remember that energy and wavelength are, by this equation, inversely related. So if the energy has to be greater than E0, that means the wavelength has to be smaller than whatever wavelength corresponds to that. Those two are, once again, inversely related. So any wavelength that's smaller than 249 nanometers will eject an electron from rhodium. So this one would work. It's smaller than 249. That one would work. So the correct answer would be both A and C. All right, so I went through that quickly, but I do encourage you to, try it on your own. Make sure you understand the implications behind that. But, one thing that people commonly forget is this inverse relationship between energy and photons. So if the energy must be larger than some certain value, the wavelength then must be smaller than the corresponding wavelength. Okay. All right, now let's talk about sort of the next observation in physics and chemistry that really threw people for a loop, which is this idea of atomic line spectra. So now we're really going to start talking about the interactions between light and matter and some of the early ideas and that came out of that about how electrons behave in atoms. So if you have white light, like from the sun or from the lights in this room, which are approximately white, and you put it through a prism, you've probably seen this before, you would get a continuous spectrum where all visible wavelengths are present. We call that a rainbow, as you're likely aware. So if you send light through a prism, or in other situations it happens too, you will get this continuous spectrum that has the whole Roy G bib, every color in between, every wavelength will be there. That's what you get for white light. However, when people started studying light that was generated by samples of elements, so the earliest experiments were done in hydrogen. You take a sample of hydrogen, you give it a real strong electric charge, and it glows, it gives off light, and then you can measure then the light that's given off by putting it through a prism. What they found was that they don't get every single wavelength. So when you take a pure substance, like an element would be the simplest one to think about, but when pure substances are energized, so typically that involves just putting a really high voltage through them, there's other ways of doing it as well, they end up giving off light. So that was sort of the observation. Not terribly surprising, but what was weird about this was that they only see a few sharp lines, or only a few select wavelengths. They don't see continuous radiation. They don't see a rainbow. They just see a few sharp lines. And so each of these lines corresponds to a discrete wavelength. And it doesn't matter how you energize the sample or where you study it, you get the same wavelengths every time. So it's characteristic of that element or substance that you're studying. So this spectrum that I'm showing here is for hydrogen, which is one of the earliest ones to be studied. And this is the hydrogen line spectrum. So when you energize hydrogen, it gives off light, but it only gives off 4 wavelengths that you can actually see in the visible region. There's other ones that are either ultraviolet or infrared, but the 4 visible wavelengths are 410, 434, 486, and 656. So you don't get every wavelength, you just get 4 discrete ones. And that was weird because, again, the expectation was that energy levels were continuous, and that if you have electrons that are moving around between energy levels to give off light, they can just give off whatever wavelength of light they so choose, but you only got a few distinct ones here. So the solution to this was proposed by Bohr, Niels Bohr, And he came up with a model of the atom to explain this. So his specifically is for the hydrogen atom. It works okay for some other things, as we'll see, but it's pretty limited. But anyway, for the hydrogen atom, which is what the Bohr model applies to, it only has certain energy levels that are allowed. So again, it's this idea that energy levels are quantized, they're not continuous. And these energy levels are determined by fixed circular orbits. So his proposal was that the electrons are orbiting around the nucleus. So the electrons are orbiting around the nucleus in fixed circular orbits. But the key point here was that they can't just be any distance from the nucleus. There's only fixed values that are allowed that it has to be at. Now his theory doesn't really explain, his model doesn't really explain why that is. It doesn't explain why the electron doesn't eventually just crash into the nucleus, as you would expect when two oppositely charged particles are close to each other. But this was his proposal, that the electrons orbit around the nucleus and there's only certain distances from the nucleus that they can be at. Alright, so that was his proposal, and then the energy of the atom does not change while the electron moves in a particular orbit. So as long as the electron is staying in that same orbit, the atom is stable. It's not changing its energy at all. And then the third point was that the electron can change to another energy level, or as we'll see, to a different orbit around the nucleus, to a different distance from the nucleus. And it does so by absorbing or emitting a photon. We'll define these more clearly in the next slide. But the point is, unless the substance either absorbs light, has light interacting with it, or if it gives off light, those are the two situations where the electron will be moving between different energy levels. Otherwise, the electron just stays in one continuous orbit, and there's no change in energy for the system. And the important thing here is that the energy of the photon that is either absorbed or emitted is equal to the absolute value of the delta E, the energy change for the atom. So whenever you see this capital letter delta here, that means final minus initial. So whatever final state the atom is in minus whatever energy it was at initially, that difference is equal to the energy of the photon that is either absorbed or released, depending on, as we'll see, the direction that the electron is going. So this was kind of the Bohr model of the atom. It's this idea of fixed circular orbits. So let's continue on with some more definitions and details about this. So some terminology that's important for the Bohr model. One is quantum numbers. So these are positive integers again, we mean 1, 2, 3, and so on, that are associated with the radius of the orbit. So as I said, you can't just have any random radius of orbit for the electron. There's only certain values that are allowed, and so they are parameterized by these integers called quantum numbers. So these are each associated with a particular radius of an electron orbit. We're not going to talk about the equation that dictates the radius of the orbit. There's an equation that dictates that, but it's not important for our purposes. But we will talk about other contexts where quantum numbers are going to come up. So these are abbreviated as N. And the radius and the energy of the electron, the radius of its orbit and its energy, both depend on N. So we'll get the equation for energy, we won't really see the equation for radius, but both of them have N as part of the equation, again reflecting the idea that the energy levels and the orbits are quantized at very specific values, not continuous. So when we say ground state, what we mean is N equals 1, and that's the lowest energy orbit. So that's going to be, as we'll see, the closest radius to the nucleus, and it corresponds to the lowest energy of the electron. So if you compare a hamburger and a steak, which one has lower energy? The hamburger, because it's in a ground state. Okay, so that's a good way to remember that one. All right, so we're getting the jokes out. All right, so then we have some things to finish, though, so we can't dwell on that for too long, but do share it with your friends if you liked it. They'll think you're cool, trust me. So absorption and emission, then, we talked about, we said those terms on the last slide. What do we mean by that? So absorption is where the atom interacts with the photon. The photon transfers its energy to the atom, and because the atom now has excess energy, it causes the electron to move to a higher energy orbit. All right, so that's what we mean by absorption. It's interaction with the photon. Photon goes into the substance, and the energy is transferred to the atom, and then the electron goes to high energy. So in this case, the energy of the photon, again, is equal to the change in energy for the atom. So however much photon energy is involved, that's going to give you the difference in energy for the electron in the atom. And in this case, that delta E is going to be greater than 0. The atom, from the standpoint of the atom, is gaining energy. It's going to a higher energy state. And in this case, then, you could say the photon is consumed, so that photon transfers all of its energy to the atom and goes away. And the other important thing is that when you have absorption, the value of n, this quantum number that associates with the electron orbit, gets larger. So as you absorb a photon, you get larger and larger in n. Okay? Emission is the opposite process. So if you have an electron at a higher value of n, something greater than 1, and it moves to a lower value of n. So in this case, the electron is moving from higher n to lower value of n. So the initial state is of larger value of n than the final state. In that situation, a photon is generated. So this is where that's how those atomic line spectra are generated in the first place. So you give a lot of energy to a sample of an element or a substance. Some of the electrons go up to higher energy because of that, and then when those electrons fall back down to lower energy, they generate light. That results in photons being generated. And again, the energy of the photon is equal in absolute magnitude, or in absolute value, to the change in energy of the atom. So those two are always closely related to each other, but in this situation, the change in energy for the atom is going to be less than 0. Okay? So you're going from higher energy to lower energy in this situation. So those are the terminology. I think what we'll close with, we have a couple slides we won't get to, but I'll just give them to you next time, is a picture of all of this. Okay? So the first thing is we have these different atomic orbits. These are not to scale. These are just random. I just picked random circles that are all equal in size or equally distributed. And again, each orbit is associated with a different energy level. So the one that's closest to the nucleus is our n equals 1 quantum number. Then we have n equals 2, and so on. So as we move further and further away from the nucleus, the quantum number gets larger. And then we can also look at the energy levels. So if this vertical scale here is energy on the right here, n equals 1 is the lowest energy level, and then they just go up from there. And as I'm accurately showing here, the energy levels get closer and closer together as you go up. So the distance between the energy levels is not equal. You have a pretty large separation between n equals 1 and n equals 2, a smaller separation and smaller, and they get smaller and smaller and smaller the higher values of n you get to. And as we said, when you generate photons, so that hydrogen spectrum that I showed you on one of the first slides in this topic, if you go from n equals 5 to n equals 2, that gives you the 434 nanometer photons. We said one of the lines that you saw in the hydrogen spectrum was 434 nanometers. That corresponds with an electron starting at n equals 5 and terminating at n equals 2. So there's no real selection for which energy levels they can move between. They can move between any of these. If you go instead from n equals 4 to n equals 2, you generate a photon that's 486 nanometers, so that's one of the other wavelengths you see in hydrogen. And then the longest wavelength in the visible is n equals 3 to n equals 2. You get 656 nanometers. Now that's not to say you can't go all the way down to n equals 1 or that you can't transfer between any other pair of energy levels. It's just that those transitions would give you photons that are either ultraviolet or near infrared. So it's only a few of those transitions that give you visible photons, but there's a whole bunch of other ones. So what we'll do next time is we'll cover the equations that dictate these energy levels and how to use them to then predict which wavelengths of light you would get when you emit from those transitions.